All right. So last time we talked about the methods that we can use to determine the equilibrium constant for reactions in aqueous solution. So we said one way was to just look it up, but that means you'll have to know what it is you're looking for. So you kind of have to know the names like Ka, Kb, Ksp, Kf. All right. Second method is just to run the reaction in the lab. Okay. Find a way to measure the activities at equilibrium, and then that will give you your equilibrium constant. You just plug it into your expression for the equilibrium constant. The problem there is because we're measuring if you're measuring concentrations in the lab, you might find your numbers are off, somewhat off from the literature values, because the ones in the literature actually do use activities, whereas when you make your measurements in a freshman chemistry lab, you just do concentrations. That's just an approximation. So don't be too disconcerted if you did an experiment in the lab, in a freshman chemistry lab, and you find that your KEQ is way off the mark. Okay, that we are just making an approximation when we're using concentrations as our activities. So in a higher level class, you'll learn a better way of doing it. Okay. Uh, Method 3 is if you know the KEQs for other reactions, you can figure out you might be able to figure out the KEQ for your reaction. And we talked about this before in general terms, so we can apply it to aqueous reactions as well. Let's just review what we said before, that if you write the reaction as A going to B and the KEQ happens to be X, if you flip that reaction, what's your KEQ? 1 over X, right? So instead of B over A at equilibrium, you would calculate the ratio of A over B. So, okay, that's what you need. What if you add two reactions together? Like this one, A going to B and C going to D. If you add these, you have A times plus C gives you B plus D. What's the KEQ for this? That would just be the product of the two equilibrium constants, right? Because K1 here would be B over A, and K2, which is our X, we'll call that X, and K2, which we call Y here, is going to be D over C. And you can see that K3, KEQ for the overall reaction would just be B times D over C times A. Okay, let me write it. Let me write it A times C. And you can identify this as K1, and this is as K2, so this is X times Y. All right, so let's apply these to the following. Suppose you wanted to know the KEQ for this reaction. H plus hydroxide gives you water. Well, this is what you get if, for example, if you have a reaction between a strong acid and a strong base. If you remember, you have a strong acid and a strong base. The H plus from the strong acid plus the hydroxide from the strong base will give you water, right? That's the net ionic equation for it. But you realize that this is just the opposite of the autoionization of water. So KEQ for this reaction, okay, for the autoionization of water is 1 times 10 to the negative 14. So what's the KEQ for this one? If you flip it, it's just going to be 1 over KW, which is going to be 1 over 1 times 10 to the negative 14. So that's going to be 1.00 times 10 to the 14. Now, look at that number. Is that a very large number, or a very small number? Very large number. So you would expect anytime you put H plus and hydroxide together in water, they're pretty much going to be neutral. You pretty much have a complete neutralization. You have your limiting reactants will pretty much be consumed. You have trace amounts of the limiting reactant. Okay. So if you have a strong acid, strong base reaction in the lab, you would expect complete reaction pretty much. Okay. So in this case, the equilibrium will be all the way to the product side because you have a very large equilibrium constant. How about this one? You have two reactions. HX gives you H plus plus X minus. The KEQ for this, you can look it up. It's the Ka of HX. Okay? And we've already seen that H plus plus hydroxide give you water has a KEQ of 1 over KW. This should be 1.00 times 10 to the 14. I made a mistake there, right? That's 1 over KW. So what would be the KB of X minus? Well, you have to know what's the reaction. If you want, if the equilibrium constant is KB, what's our reaction? The base is X minus. If it's behaving like a base, it should be reacting with what? Base is a proton acceptor, so it will be accepting a proton from water. So the reaction we're interested in is between X minus and water, giving you, if it's behaving like a base, it's to generate hydroxide, and it should accept a proton from water, giving you HX plus OH minus. So how can we combine these two reactions to give you this reaction? Think about something similar to Hess's law, right? What would that be? You want HX on the other side, right? So you reverse the first one, so you write the first one in reverse. So you have H plus X minus gives you HX. What's the KEQ for this? It's going to be 1 over Ka of HX, right? You're flipping that one. And then you keep this one as is. Oops, do you flip the other one too? This one. Yeah, you flip it too, right? You want hydroxide on the product side, so you flip that one. So you write H2O. Let me write it in black. H2O yields H plus X minus. You want H2O on the left side, see? H2O plus, H plus hydroxide. What's the K for this? That's just KW, right? So if you add these two, what do you get? Overall reaction is H plus cancels out. So you have H2O plus X minus, which is what you want on the left, right? Yields HX plus hydroxide on the right. So what's the equilibrium constant for this? Equilibrium constant for this is called the KB of X minus, and that's equal to what? The product of this and that, right? So it's KW times 1 over Ka of HX. Okay? So generally what you find is this. Let's rearrange this. Let's put these two together. You'll find that if you have KB of X minus, you multiply that, now that's equal to KW over the Ka of HX. Okay, in other words, if you multiply the KB and the Ka for a conjugate pair, you get KW. Okay? So Ka of an acid times the Kb of its conjugate base will give you Kw. Or if you take logs, pKa plus pKb will be equal to pKw. And what's pKw? 14, right? Remember, Kw is 10 to the negative 14. Negative log of 10 to the negative 14 is 14. So the pKs will add up to 14. The product of the Ka and Kw would be 10 to the negative 14. It's going to be equal to Kw. All right, so let's illustrate that with this. Before we do, let's illustrate that with this first, and then we'll come back to that one. Ka of acetic acid is 1.8 times 10 to the negative 5th. What is the Kb of its conjugate base? What's the conjugate base of acetic acid? Acetate ion, right? So what do? We just say Ka times Kb is equal to Kw. So Kb would be Kw divided by Ka. What's Kw? 1.00 times 10 to the negative 14. And what is Ka? 1.8 times 10 to the negative 5th. that should give you 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5 equals 5.55 times 10 to the negative 10. It's 2 sig figs, so 5.6 times 10 to the negative 10. Okay? Got it? Okay. So here's a clicker question. Which of the following is equal to KW? Oops, what happened to my clicker? There it is. Okay, anytime you're ready. Which of these is equal to KW? What's another way of asking this question? This is all KA times KB, right? But the answer is not all of the above, obviously, because I did not give all of the above as a choice. So what's another way of asking this question? Which of these is an acid-base conjugate pair? A conjugate acid-base pair. Okay, let's see how we did. B is a popular answer. Oh, very good. Thank you. Okay. If HCO3 behaves as an acid, then the conjugate base would have one less hydrogen and one less charge, right? HCO3 and HCO3, that's not a conjugate pair. H2CO3 and carbonate, that's 2 hydrogens difference. That's not a conjugate acid-base pair. Okay, so the correct answer is B. All right. How do we explain why sodium acetate is basic? Well, acetate, we say, is the conjugate base of a weak acid, so it's also a weak base. In fact, we just calculated that earlier, right? Its Kb is 5.6 times 10 to the negative 10. So it can react with water to give you acetic acid, HC2H3O2 plus hydroxide. Anytime you're asked to explain why something is basic, look for a reaction that will generate hydroxide. So the way you would explain this, if you went to the lab, you measured the pH of this salt, you'll find it's basic. Okay? And so the way you would explain it is by saying, okay, the negative ion here, the anion, is a conjugate base of a weak acid, so that will react with water to give you hydroxide. And that makes it basic. That's how you explain basic salts. Okay? Now, based on that, the Kb of chloride ion is A, very, very large, or B, very, very small. To help you with this, what is the conjugate acid of Cl minus? HCl, right? What is the Ka of HCl? HCl gives you H plus chloride. What did we know about HCl? It's one of the 6 strong acids. So what's the Ka for this? Keq for this reaction is very large, right? In fact, it is so large that we generally just ignore it. We just say, oh, anytime you have HCl in water, we're just going to dissociate it completely. So this Ka is very, very large. So given that the Ka of HCl is very large, what do you expect the Kb of chloride ion to be? Okay, it's got to be very, very small. In fact, chloride ion, okay, if I were to ask you, why is a sodium chloride solution, why doesn't the chloride ion make your water basic? You would say this reaction right here, where chloride reacts with water to give you HCl and hydroxide, okay, this doesn't happen at all, okay? Hardly ever happens. because your chloride is a very weak base. Okay, so it cannot pick up a proton from water. HCl is a very strong acid, so it's not going to stay as a molecule in water. So the correct answer for this is B, very, very small. Which of the following has a larger Kb? Nitrite or nitrate, A, or B, nitrite? Which one has a greater tendency to pick up a proton from water? Remember, a base is a proton acceptor. Why would I expect you to know this? Let's see. Okay. Nitrate. What's the conjugate acid of nitrate? HNO3, right? And the conjugate acid of nitrate is HNO2. Which of these is a strong acid? This is a strong acid, right? You have to remember your 6 strong acids. There's only 6 to remember, so memorize it. HNO3, HCl, HBr, HI, H2SO4, and HClO4, perchloric acid. Those are your 6 strong acids. So if HNO3 is a strong acid, and HNO2 is not one of the 6, so HNO2 would be what? It's a weak acid, right? Then, do you want to change your mind? You sure? It's going to be a very, very weak base, okay? So if it's a strong acid, it's going to be a very, very weak base, okay? The conjugate of it is going to be very, very weak. So nitrate, you're going to say, it's not going, if you have a nitrate salt, that nitrate's not going to make it big. Will have no tendency to make your solution basic, okay? The cation we've talked about before might make your solution acidic, right? Cations, except for those from group 1A and 2A, have a tendency to hydrolyze and make your solution acidic. Here we can see that negative ions can make your solution basic, provided that they are not one of these anions from these 6 strong acids, okay? Now, pKa and pK1 and pK2 of carbonic acid are 6.35 and 10.33. Do you expect sodium bicarbonate to be acidic or basic? First of all, sodium's not going to hydrolyze, okay? So you can ignore the effect of sodium, group 1A. Okay, it's not going to make your solution acidic. But bicarbonate can make your solution acidic or basic based on these 2 reactions. The question is, which one? Well, let's look at bicarbonate acting as an acid. What's the Ka for this? That's going to be the K2, right, of H2CO3. And if I'm given pK2, what is K2? If pK2 is 10.33, then K2 is 10 to the negative 10.33, right? 10 to the K2 is 10 to the negative pK2. So this is 10 to the negative 10.33. So what is that? Actually, I don't even have to evaluate that, but if you want to do that in a calculator, what do you do? 10.33, 10 to the negative, right? And then 10 raised to the power x. So that's going to be 4.7 times 10 to the negative 11. Okay. What about this one right here? What's the KEQ for this one? What do you call the KEQ for this second reaction here? Your bicarbonate's picking up a proton from water, giving you hydroxide, right? This is the Kb of bicarbonate. Okay. So am I giving you the Kb of bicarbonate? I'm not. I'm giving you K1 and K2 of carbonic acid. But if you recall, this is Kw divided by what? The Ka1, in fact, of H2CO3, right? Kw times Ka for a conjugate pair, we just talked about that, is equal to Kw. So this is 10 to the negative 14 divided by, what is pK1? K1. Ka is 10 to the negative pK1 is 10 to the negative 6.35. 10 to the negative 6.35. It's 10 to the negative pKa1. pK1 is the same thing as pKa1. You're given pK1. Okay. pK1 is 6.35. Therefore, K1 is 10 to the negative 6.35. P something means negative log of something. Okay? So what's 10 to the negative 14 divided by 10 to the negative 6.35? So that's 10 to the negative 14 minus negative 6.35. Okay? So negative 14 minus minus, so that's plus 6.35, negative 7.65. Okay. And what's the antilog of 10 to the negative 7. What is the antilog of negative 7.65? So 10 to the negative 7.65 would be 2.2 times 10 to the negative 8. Okay, so let me fix that. This is 10 to the negative 7.65, which is equal to, how much is it? 2.2 times 10 to the negative 8. Okay, so here we are. We figured out our KEQs. This one, oh, what did I just do? Okay, this is 10 to the negative 10.33, or what was it? You have a number for me? What is it? 4.7 times 10 to the negative 11. Okay. And the second one, we just figured out, that's the KB. And that is what? 2.2 times 10 to the negative 8, right? So it's 10 to the negative 7.65, which is the same thing as 2.2 times 10 to the negative 8. So you're looking at two competing processes, one generating H+, the other one generating hydroxide. Which one wins? Which one will go farther to the right? The one with the larger KEQ. Which one has the larger KEQ? The first reaction or the second? Second reaction. So if you went to the lab and I asked you to measure the pH of a solution of sodium bicarbonate, what would you expect to get? Acidic or basic? You'd expect it to be basic. Okay? So sodium bicarbonate would be a basic salt. So why is sodium carbonate basic but sodium chloride is not? Then they both have sodium, so the difference must be in the carbonate and the chloride, right? So what do we know about carbonate? If you want to explain why it's basic, you have to write a reaction that shows it forming hydroxide. So it has to pick up a proton from water, gives you HCO3 minus plus hydroxide. Okay? And so what's the Kb for that? Actually, we have the Kb. It's it's going to be equal to Kw over the K2, right, of carbonic acid. Why K2? Because K2 of carbonic acid is the Ka of HCO3 minus. So we have that earlier. K2 is 10.33, okay? So that's 10 to the negative 14 over 10 to the negative 10.33. That's so that would give you 10 to the negative 14. So 14 negative minus minus, so that's plus 10.33. 10 to the negative 3.67. Okay, so that's a relatively decent Kb. That's 2 times 10 to the negative 4. Okay, but the key here is that it produces hydroxide. What about chloride? What do we know about chloride? What happens? Let's try to make it a base. It'll pick up a proton from water, which gives you HCl plus hydroxide. Okay, you cannot make HCl in water because that's a strong acid. Okay, so the KEQ for this, the KB for this is going to be very, very, very small. For practical purposes, we say it's a neutral. That ion is neutral. Okay, it's not going to give you any hydroxide in water. Okay, here's another question that we can apply, where we can apply the method of determining equilibrium constant from other values. The complex ion formation, for complex ion formation, if you look up KEQ for these reactions, they're usually tabulated. You might find it tabulated as log of the KF instead of negative log KF. And the reason for that is KF typically is a large number. Okay, and so if you take the log of KF, you get like a whole number, positive whole number, so you don't need to put a negative in front of it. So instead of PKF, they're tabulated as log KF. So for example, the log KF for silver amine complex, okay, AgNH2 with a positive 1 charge. If you look it up, you'll find that to be 7.05. Okay. You can also look up what are known as stepwise formation constants for this complex ion. The first step is you just pick up 1 ammonia, okay, and you can look up the log for that to be 3.24, log of the equilibrium constant for that. And then if it picks up another ammonia molecule, so now you have AgNH2, okay, there's another formation constant for that. The question is, what's that number if the overall formation constant is 7.05? How can we calculate log K2? Well, let's look at these two reactions. What happens if you add these two reactions? Let's combine them. You have Ag plus, what happens to this one? It cancels out, right? So this just gives you 2NH3 aqueous, okay? Aqueous gives you, your product is your silver amine complex AgNH3 plus 1 charge. What's the KEQ for this one? It's equal to the product of K1 and K2, right? The KEQ for, what's KEQ for this first step? K1 is equal to 10 to the 3.24. Okay? And for the second step, K2 is equal to, we don't know. But what is K for the overall reaction? Kf is 10 to the, it's given, it's 10 to the 7.05. Okay? If you're given Kf, if you're given log of Kf, how do you solve for Kf? Here. Log of Kf for the overall reaction is 7.05. Therefore, Kf equals 10 to the 7.05. See? So Kf is 10 to the 7.05 is equal to K1, which is how much? 10 to the 3.24 times K2. So you can solve for K2. K2 would be equal to what? 10 to the 7.05 divided by 10 to the 3.24. So that's equal to 10 to the 7.05 minus 3.24. Remember, 10 to the x over 10 to the y is the same thing as 10 to the x minus y, right? So that gives us 7.05 minus 3.24, 3.81. 10 to the 3.81, and if you want an actual number for that, that's easy to see, to visualize. You take the 10 to the 3.81, take the analog, you get 6,456. Okay? So this has 2 decimal places. My answer should have, and taking the antilog, your answer, the number of significant digits in your answer should be the same as the number of decimal places in the original number. So that would be 6.5 times 10 to the third. So that would be the equilibrium constant for the second step in the formation of the silver amine complex. Okay, so let's take a look now at some applications. Okay, all of these. One of the more important things you want to be able to do, given all of the information, okay, given initial concentrations or activities and the value of the equilibrium constant, is how far will the reaction go? Okay, that's the most common question you'll be trying to answer with problems pertaining to equilibrium. How far will it go? And that means what are the values of the concentrations at equilibrium? Okay. So the generic procedure is set up an ice table, list the initial concentration, tabulate the changes in terms of variable extent of reaction x, and then express the equilibrium concentration in terms of that variable x, right? Compare Q versus KEQ to determine whether it's going to go forward or reverse. Okay, so we're going to let x be the extent of reaction, and solve for x, knowing that Q must be equal to KEQ at equilibrium. That's the generic procedure. And usually, in this last step right here, when we solve for x, we try to look for a way to simplify our calculations, because more often than not, we're going to get polynomials, quadratic equations. So if we can find a way to get an approximation, that would be good. Okay. And so you need to look out for very large KEQs or very small KEQs. Because if you have a very large KEQ, what does that mean? You can assume everything. You can imagine everything going all the way to the products except for the excess reactants, and then you have a trace amounts of limiting reactant left. Okay. Or if it's very small, then you can imagine the reaction shifting all the way to the reactant side. Okay, so that makes things a lot simpler. And in fact, for most of your exam questions, that's probably what you're going to get, because you're not going to be expected to solve a cubic equation on a 1-hour test, along with other problems. Okay, so let's take a look at this question right here. What's the pH of a solution of 0.1 molar HX if HX is a strong acid? So what's a possible identity for HX here? It could be HCl, HNO3. What are the 6 strong acids? HBr, HI, HClO4, and H2SO4, but this is diprotic. Okay. So anyway, if you have HX, so what do we know about H+? It's just going to be all of this HX. So what's our reaction? HX goes to H plus X minus. You start with how much? 0.1. What would be your changes? So let's assume you have 0 for those. What will be your changes? Minus X plus X plus x. What would you have at equilibrium? 0.1 minus x, x, and x. Since we know that Ka here, you don't even have to look up the Ka for Hx because you know it's a strong acid. It's very large, right? What can we assume then? It's going to go all the way to the product side. So this will be essentially 0. You'll have a trace amount left, right? And so this will be essentially 1, 0.1, and this is going to be 0.1. X is going to be 0.1. So what's our pH then? H plus is going to be equal to 0.100. And so what is our pH? Negative log of H plus. So take the log of 0.1. What would that be? 0.1. Take the log, take the negative. So that's going to be 1. So negative log of 0.100 is equal to 1. Okay. Do I have the right number of decimal places here? Sig figs. When taking the log, the number of decimal places in the log must be the same as the number of sig figs in the original number. So three significant digits in H plus, your pH should have 3 decimal places. So your pH is 1.000. Okay. Now, let's look at this question. It's a similar question. HX is still a strong acid, right? So can we just say H plus is just going to be 1.00 times 10 to the negative 8? All of your HX is going to dissociate, right? And so what would your pH be? Minus log of 1.00 times 10 to the negative 8. That gives you how much? 8, right? Three decimal places, 3 significant digits, 3 decimal places. Wait up. You've got an acid and you got a basic pH. This is a basic pH. It's not going to work. What have we been ignoring? What did we ignore in the last calculation? And we're also ignoring it here. We're ignoring the fact that water itself produces H plus. And pure water will give you 10 to the negative 7. This is only giving you 10 to the negative 8, so you cannot ignore the autoionization of water. So you have to take that into account. So this is wrong, okay? So what you need to do then is examine how this will affect the autoionization of water. You have H2O, gives you H plus plus hydroxide. What is our KEQ for this one? 1.00 times 10 to the negative 14, right? So you need to examine this equilibrium. What would be our initial conditions here? Let's just pretend your water is all on the your H plus is what? 10 to the negative 7, right? And 10 to the negative 7, and your water, you have an excess of water. That would be what you would have, right? And then you add more H plus, 10 to the negative 8. So plus 10 to the negative 8, okay? And you're not adding any hydroxide. So Le Chatelier's principle says, what will this cause? You're adding more H plus, you're adding more products, your equilibrium shifts which way? To the left, right? Equilibrium shifts to the left. So you're not going to get 10 to the negative 7 anymore, right? From the autoionization of water. So let's just say we're going to get X for that instead of 10 to the negative 7. Okay, so your changes for water would be just plus X and plus X. Okay, so your at equilibrium, what you have would be H plus would be 10 to the negative 8 plus X, and your hydroxide would be X. Okay? And you know it's not going to be 10 to the negative 7 because Le Chatelier's principle says it's not going to go as much, it's going to shift to the left. So we now have an expression for H plus and hydroxide at equilibrium. Let me just call this letter B to make things, so I'm going to call, to make things easier to work out later. So this is called 10 to the negative, 10 to the negative 8, right? So that's the concentration of the strong acid. So we can say then that H plus times hydroxide is equal to Kw, right? So we say then B plus X, okay, times X must be equal to Kw. Can I solve for X? Let's rewrite this. This is X times X is what? X squared, right? X times B is Bx, distributive property, and I'm going to move this all the way to the left side, so minus Kw equal to 0. How do I solve for X? We have a quadratic equation here. Ax squared plus Bx plus C is equal to 0. How do you solve for X in a quadratic equation? Negative B plus or minus square root of B squared minus 4AC over 2A. Okay? So that's one of those formulas from math that you should remember. So this is going to be negative B plus or minus square root of B squared minus 4. What is our A here? A is 1, right? And what's our C? Negative Kw over 2A, so over 2. So it's going to be negative B plus or minus square root of B squared plus 4Kw over 2. So what have we been assuming? What did we assume in the earlier calculation that we did? We're assuming that B is negligible, right? I mean, not B. X is negligible, okay? And what you'll find if you solve this equation is that X is in fact not negligible compared to 10 to the negative 8. So you'll actually end up with a pH that's actually between 6 and 7. It's still going to give you an acidic pH, okay? So what you really need to do here is compare B squared and 4 times Kw. What's 4 times Kw? That's 4 times 10 to the negative 14, right? And what's our B squared? 10 to the negative 8, okay, squared. Okay, that's 10 to the negative 16. I lost track of what I was about to say here, so just forget it. Forget what I just said. There was something I meant to do here, but I lost track. So the idea here is you can solve for X. Now, you'll notice you have two possible values for X because this is plus or minus, right? So if you get a positive value for X, that would be the reasonable answer. If you get a negative value for X, that's unreasonable. Okay, so you only take the positive root in this particular case. All right. How about this problem right here? What is this pH of a solution of 0.1 molar HX if Ka of HX is 10 to the negative 5th? 1.8 times 10 to the negative 5th. Oh, before that, by the way, let's go back to that earlier calculation we did. Remember we said H plus was supposed to be 0.1 plus X, right? And what do you notice about, okay, over here? X is really just the hydroxide concentration too, right? Correct? So, once you get your X here, you get your hydroxide concentration, and then from that you can get your H plus concentration. So, X is really just the hydroxide concentration. What's our hydroxide concentration here in this original problem? It's 10 to the negative 14 over 0.1, right? which is going to be 0.100. So it's going to be 1.00 times 10 to the negative 13. That's your x, right? Is that negligible compared to b? Our b in this case was 0.100. So our h plus, okay, we said was 0.100 plus x, and we just said that that x right there is negligible. In fact, is it negligible? 10 to the negative 13 compared to 0.1, you can pretty much ignore that, right? So that assumption is okay. As long as your pH is significantly away from pH 7, you should be okay by making that assumption. All right, let's look at this one. 0.1 molar HX, but this time HX is a weak acid, and you're given the Ka is 1.8 times 10 to the negative 5th. This is, in fact, the Ka of acetic acid. So let's solve this problem. You have HX gives you H plus X minus. What's our initial condition? 0.100 molar HX. Assume negligible concentrations of H plus and no X minus. What would be your changes? Minus X. It's going to go forward, right? Plus X plus X. So our equilibrium concentration would be what? 0.100 minus X, X, and X. How do I solve for X? I'm going to say that X squared, okay, Ka, is H plus times X minus over HX. So it's going to be equal to X times X over 0.100 minus X. Okay, and what is my Ka? It's given as 1.8 times 10 to the negative 5th. So you have a quadratic equation here. Okay, so you solve for, work out the algebra and solve for X. Can we simplify? No, because this is 0.1 minus X. So that's X squared over 0.1 minus X equals 1.8 times 10 to the negative 5th. I'm going to write it this way so you don't confuse that times with X, okay? So you have to solve for X there. You can use a quadratic equation, but we can make a simplification. Given that this is small, you can assume that 0.1 minus X is essentially going to be 0.1. Negligible compared to 0.1. Is that a valid assumption? You have to check in the end. If not, then you're out of luck. You have to go back and actually do it using quadratic equation. But let's say that X is in fact small enough. What would it be? Then you would say X squared over 0.1 would be equal to 1.8 times 10 to the negative 5th. And so what would be my X? This is easier to solve now. I can say X squared equals 1.8 times 10 to the negative 5th times 0.1, which would be how much? 1.8 times 10 to the negative 6, right? That's my X squared. So what's my X? What's the square root of that? 1.8 times 10 to the negative 6, and then take the square root. How do I take the square root here? Raised to the power 0.5. Oh, here. The second root. Yeah, 0.0013. So it's 1.34. 1.3 times 10 to the negative 3. Okay, 0.0013. That's my value for X. Is that negligible compared to 0.1? Compare this one. This is 0.0013, and this is 0.100, right? So this is 0.100 minus 0.0013. How much error am I making by making that assumption? My error would be over here in the third decimal place, right? That's 1 part of 100, 1% error. you're within, if you can get it to about 10% error or less, you should be okay for most practical purposes, okay? So you would say that's a reasonable assumption. So we'll go with that, okay? So what would be our x then? Our x is 1.3 times 10 to the negative third. So going back to the question, we now figured out what our x is, right? We figured out that this is equal to 0.0013. That's 0.0013. So what's our pH? pH is negative log of H plus at equilibrium, negative log of 0.0013, and what's our pH going to be? 0.0013, take the log, 2.89, okay? So our pH is 2.89. Okay? That's your pH. What would have been the pH if this was a strong acid? If you had a strong acid, X would have been 0.1, right? And so that would have been your H plus, and your pH would have been negative log of 0.1, which is 1. So you see, it's not quite as acidic as we would expect a strong acid to be. So if you have to compare two acids, two monoprotic acids, one strong, one weak, if they have the same concentration, which one would have a lower pH? The stronger acid would have a lower pH. The strong acid would have a lower pH. Okay. Oh, here's a clicker question. Looks like I just primed you for this question. Which is a solution of a strong acid? 0.1 molar HY, pH is 2. 0.1 molar HZ, pH is 3. Both or neither. Now Y and Z are fictitious, okay? HY and HZ. So don't say that neither one is strong because it's not one of the six. Okay, this is fictitious. But be open to the possibility that that fictitious acid could be strong or weak. So what would it be? Right? I just told you that don't pick D. Not necessarily D. All right. So if it was a strong acid, actually, if it's a strong acid, what would have been the pH? Minus log of 0.1, pH would have been 1. So neither one is a strong acid. So actually, D is correct.
Wait.
It's not necessary.
I picked D, but then you told the answers you said. I just told you guys not to pick D.
I'm sorry. Not necessarily D. Sorry. I'm sorry about that. Yeah, it is. It's neither one. Both are weak. Okay. Which one is the stronger acid? HY would be the stronger acid. Okay. So the correct answer was in fact D. Neither one of these two is a strong acid based on our definition of a strong acid is. But if I ask you which one is a stronger acid, that means I'm not necessarily saying it's strong. It's just stronger than the other, comparing the two. All right. What's the solubility of MX2 if its KSP is equal to 1 times 10 to the negative 10? So how would you set up this problem? This might be a good time to take a break, huh? So let's continue that in the next time.